actually. The announcement is we are, I think, ready for a data scientist position, so reach out to Richard. The paper is titled Program Language Translation Using a Grammar-Driven Tree-to-Tree Model. This was presented at ICML a couple weeks back in Stockholm. And it kind of builds upon another paper by Chen, Liu, and Song. This one was rejected from the main track of iClear 2018, but it actually kind of was presented at the workshop track. And actually, in my opinion, I have some choice work for the authors of the actual paper that I'm presenting this one. But this one's actually a way better paper, so I don't know how these things work. But in terms of at least the experiments, and kind of. They kind of sort of, this paper, how it differentiates itself from that tree-to-tree neural nets is based on or inspired by the work done by the second paper, syntactic neural model for general purpose code generation, and kind of architecture-wise, if you will. The third paper and the fourth paper are kind of very they're referenced and they're definitely used in designing the architecture and the algorithm. Effective approaches to attention-based neural machine translation. This one's from ACL 2015, if I remember correctly, and the other one is improved semantic representations from tree-structured long short-term memory networks. And this is the basically the main tree LSTM paper. So tree LSTMs come from the fourth paper. The third paper is not as novel, I would say, but basically kind of formulated and conceptualized different types of attention and attention mechanisms as they pertain to like NLP basically, or even like more general NLP, sequence to sequence. I had a very interesting discussion with Ed, and my original plan was before starting the talk. My original plan was going a little bit into the problem, because basically the problem is we want to create a transpiler from based on end-to-end data-driven training principles. Now, why would you want to do that? In my opinion, it's still an open question that is not well addressed by all of these contributions, because compiler generation or compiler theory is probably as old as computer science itself. It's been around since like mid-50s at least. All the parsing theory, context-free grammars, context-sensitive grammars, attribute grammars, like code generation, all of it has been like completely automated, supposedly. Though actually, if you look into the source code of any modern compiler, you see that a lot of that theory doesn't really apply. So a lot of it is, even the parsers, like parsing theory, as I said, is probably as old as like, computer science itself, pretty much. There's an apocryphal story. I like it to be about Don Knuth. I think it's about Don Knuth. So apparently he, on his honeymoon, he actually read a paper from Chomsky. And that kind of ignited the whole thing. He thought about like, programming language translation from actual high-level languages to like, to assembly in terms of Chomsky's theories of grammar. And ever since then, these two subjects have been going hand in hand. So it's a very well-trodden ground. But also, somebody, I think in the early 90s, called the parsing and syntax-directed translation problem the biggest solved problem in computer science theory. So it's one of those problems where theory is supposedly guiding practice, but the fact of the matter is practitioners never use the theory the way it was intended to be used. You have to, like, if you want to write a compiler front end, you have to morph the grammar of your source language into a family of subtypes of grammars for which we can actually efficiently generate parsers. So we have the general CFG grammars, and then there's LL and LR with all the different look-aheads, and even none of them actually even capture any of the realistic programming languages. It's always there's a degree of context sensitivity, and the actual context-sensitive grammars of the 1960s and 70s never actually took hold. So you have to you have to basically adorn your code with a lot of data structures, with a lot of bookkeeping, and there's a lot of dark magic actually goes into writing a compiler. And the whole neat and tidy pipeline of lexical analysis, syntactic analysis, and ASD to or CSD to ASD code generation, tree traversal. A lot of it is basically, in fact of the matter, actually BS. There's a lot of branches going all over the place in the pipeline. There's a lot of places where you actually have to refer back. If you add, like, if your language is, for example, OOP, if it's object oriented, you actually have to have a facility to let your legs that are front end actually use the new types that you define as new types of tokens as opposed to variable names and identifiers. So there's a whole lot of things that are not really the way they are in theory papers. So in my opinion, this is a problem that is really ripe for disruption by end-to-end training models. Also for the fact that optimization, code optimization is really a huge part of a lot of compilers these days. And code optimization, if compiler front end is actually black magic, compiler backend is black magic to infinity. Like nobody other than the people that write the compilers knows how the backends work. And there are many phase ordering problems, many things that basically even like the slightest change and the slightest deviation from the stated assumptions means that your compiler backend generator is going to generate like incorrect code, and if that code happens to be used in some, I don't know, nuclear reactor or some other health and safety critical use, then gods of computing help you. So
Alex,
yeah,
just because you made a few points, just a quick question and a follow-up quick question. When you say context sensitive, you mean, I'm just saying it for the audience. You mean that from the production perspective, if you have nodes or elements on either side of the letter to be written, then it would generate a different type of node. Okay, so that's what you meant. Okay.
The type of tree expansion can actually depend on the left side console. So yeah,
left side.
Your productions are not non-terminal string of terminals and non-terminals.
And that's a challenge for today's work because they're using context-free grammar only?
Yes. Okay. So they're using a context. So there's in a sense they're using a context-free grammar as an inductive bias to their algorithm, but obviously the end-to-end training, the data-driven training is supposed to give them context, because obviously you can't translate a tree, like a global tree of a program, consistently from local actions if you don't have some context sensitivity. But the context sensitivity is relegated to the data-driven part, so that's not something you kind of enforce or you put into the structure of your algorithm. So and basically, so they actually build up the use case pretty much by saying that it's programmers can write programs in whatever language suits them, and they don't have to worry about the glue code or like all the different versions and whatnot, and the results definitely disappoint if that was the intention. And one of the demonstrative examples that they use is a CoffeeScript to JavaScript translator. Now, CoffeeScript, for those of you, I'm not a front-end developer, so my knowledge is very limited, but apparently it's like the non-retarded cousin of JavaScript, so it's already kind of a JavaScript plus. So that task itself is kind of hard to justify on the assumption that general translation is a very hard problem. But regardless, their testing and experiment design doesn't even support that use case. So yeah, kind of to the points I was making, but more about the general background. So programming language to programming language translation is generally, could be, the simplest case could be infix to prefix mathematical expressions. So arithmetic expressions using plus, minus, multiplication, division, to prefix format, which is kind of, in a sense is like very native for like stack machines. So that could be some kind of code generation. From a high-level language to an intermediate representation, from imperative to functional, and the use case that they really emphasize, which is its use in IDEs and tooling. And one of the problems, so translation, as I said, is one of those problems that has been solved supposedly for 40-something years or 50-something years, but it's definitely one of the biggest solved but unsolved problems. So for example, if you have grammar for language A and grammar for language B, and you have a tool like, for example, JSX, like, you know, HTML, templating within JavaScript code, there's no way to kind of, you know, there's no function, there's no theoretically justified way of feeding these two grammars into a parser generator and getting something that is enabled to unambiguously parsing the combined language. So there's a lot of transformations, a lot of ad hoc and domain knowledge that you have to use to actually create a grammar that can actually parse like HTML in Python and HTML in JavaScript, whatever you might actually have. So so it's not a solved problem by any stretch. And they kind of basically build up the use case of computer-aided software engineering, so using automatic tools for solving these problems. So and the idea, as is generally the idea in any sort of neural machine translation, is an encoder-decoder architecture. So you have the source and you have the target. You encode the source successively or in some order, and you get a general encoding plus some attention mechanism, and you start your decoding loop, which is basically combined attention. So at every step, you know which part of the encoded source you have to pay attention to, plus some sort of reverse of the encoding operation. And obviously the benefit of using this is it allows for end-to-end data-driven training. So if we have a, I don't know, a treasure trove of programs compiled using GCC to some intermediate for, or some yeah, whatever format, or transpiled from like CoffeeScript to JavaScript or TypeScript to JavaScript, we can basically use those as input-output pairs and learn a lot of things. And by a lot of things, I mean optimizations, constant folding, a lot of different things, or a removal of things that are not used, so decode elimination, a lot of things that people that write compilers really care about and are really hard to get right. And also stylistics and stylometric conventions as well. So if you're thinking both source and target being high level, where you're not erasing identifier information and naming conventions and even code organization conventions, this is something that no compiler or transpiler is going to give you. So you can't preserve style, you can't preserve naming conventions, because as far as the compiler is concerned, there's no such thing as style or naming convention or organization of code or like tabs or spaces or what have you. So this is supposedly able to take care of that as well. And the problems, as I alluded to, the problems of using a data-driven approach is that formal languages are not free-form. Natural languages, you have some latitude in how you can phrase stuff. You can kind of, you can have very stilted phrasing and still be understood, whereas a compiler is, or any sort of consumer of a formal language is a much more unforgiving receiver of that information. So you have to generate programs that are syntactically correct. There's no way around that. And existing data-driven end-to-end, trained statistical machine translation approaches are oftentimes not up to that task. They just generate a lot of random and invalid outputs. And if you've seen Andrzej Karpathy's, I don't know how many of you have heard of Andrzej Karpathy, probably many here. If you've seen his examples of generating or using a LSTM generator for and running that on Linux source kernel, you can actually see that point pretty well. It's a very kind of incoherent mumbling and non-compiling code. It kind of vaguely looks like file system code in some places, but it's basically complete complete BS. It's not actual code that would ever actually do, not compile, that would ever actually do anything useful. It just kind of goes through a lot of conceptual things and things that superficially look like they're actual functioning code, but they are not. So we want to incorporate the strong inductive bias of syntactic validity. So we want to make sure that we're generating stuff that do make sense. If we are, and in a sense, do make sense in
if they're defining a variable, they're going to use it. They're not going to, there's going to be some logical flow to the program. There's going to be, you're not going to just randomly sprinkle like, some file system code, some block management code, and whatnot. And I'm using a lot of terminology from Linux kernel because that's one of the examples that I think a lot of people might have seen here. So we want a code a code generation procedure that is actually kind of working towards the goal as opposed to just generating stuff that is locally plausible but not really doing anything.
Can I ask a probably stupid question? So one solution that comes to mind for the last one, which is something that they use for natural language and chatbots, because that also, like, as you go down the conversation, becomes garbage very quickly. So what they would do is just put in templates, and then the generative part is essentially filling the blanks, right?
Yeah.
So do you know if there are approaches that essentially build the structure and then fill in the blanks for this task as well?
That is a very good observation. I hadn't thought of it. I don't know of any approaches, but it could be like if you're using this kind of network for like generating glue code or like interface code or like general data transfer, data translation from one format to the other, like the type of thing that people use like protobuffs or like IDLs for, that could probably be very useful. Like literally, you can probably capture the entire space with like 16 or 17 templated pieces of code, and then like fill in the blanks and find the intent and like fill up all the slots and whatnot, and it should probably work pretty well. I haven't seen that used, so that's you can write it up and submit it somewhere. If it definitely, yeah.
It's the first TDLS paper.
Yeah, and so but this is basically more kind of just open-ended, general, like whatever. Like we have a snippet of code in programming language A. We want to convert it to programming language B. So basically, refinement from general neural machine translation. So where you actually have a sentence encoder and then a corresponding decoder. The refinement that they propose, and it's not them, it's actually like the other paper that I referred to, is to use tree-structured recursive neural nets to deal with the tree structure of formal languages. So, and if you use it judiciously in generating your output, you can use that to enforce your syntactic validity as well. And basically, this is the example. This is kind of the example that they basically went with, and they build up the entire paper. So the left side is a CoffeeScript program, and the right side is the equivalent, just plain JavaScript. And they're kind of calling attention to the fact that you have, for example, an if statement, and the condition of the if statement basically happens between the statement itself and the block that gets executed if that condition is true. So there's arbitrary displacement from where you see the if keyword to where you see the actual block that you have to execute. So if you're using just a linear like chain LSTM or any kind of network, there's some chance that you're going to lose the local context. Now, to what extent that's a valid argument, I don't know, but they actually have some convincing simulations. So they use a plain linear sequence-to-sequence model. It doesn't really perform anywhere near close to both theirs and the paper they're basically basing their work on. So there's the argument to be made that if the encoder-decoder structure respects the tree structure of your source and target languages, there's much better opportunities to learn from data with smaller number of parameters.
Is the goal here to translate from the colored part to the colored part, or the whole thing?
No, the whole thing is basically so this one was if y triple equals 0, x equals 1. So this is assign 1 to x. And this is the equivalent, like, so yeah, this is like this is a very contrived example because basically CoffeeScript and JavaScript for this don't really differ that much. But then again, assign is basically a assign expression. Probably CoffeeScript, I don't know, I'm not a front-end developer. If anyone here has that experience, I don't know, maybe, I'm guessing this expression statement means that CoffeeScript is probably less functional or less, has a distinction of statement versus expression where, you have to put this node. But apart from that, I don't see much of a difference. So it's kind of, yeah, it's a very contrived example because even like down to the actual characters, the source and target are basically the same.
So what's the significance of it being colored?
The significance of it being colored is, I think, the fact that when you're generating this part, if you're concentrating on this part, the colored part, we have to, and honestly that argument doesn't really go through, but we have to like consider the fact that it's one branch of an if statement, so it's the block that actually gets executed, and the tree structure lets us see this, but regardless, even like an actual non-tree structure, like x equals 1 is x equals 1, so we get all the locality that we want. So I don't see how that kind of helps the argument. But that's, I mean, in general, like this is a very, and to be fair to the authors, in the interest of space, it's really hard to kind of create like arbitrarily nesting structures where like that displacement is real. But I think everybody that has written any code in any imperative programming language has that experience of you have, and it's generally code spell, but you have like a very complicated branching, like if else or switch case statement as the case might be, and 3 levels deep you don't even understand what the dependencies are, or you finish one case and then you don't know what you should do. So that is definitely a disconnect that is real. So you're losing some context.
So one of the transpilers, or popular ones, is TypeScript to JavaScript.
Yeah.
Where the advantage that TypeScript gives you is that it provides you static typing over a dynamically typed language.
Yeah.
So how would that, like, how do you infer a type from a dynamic type from a static type? Would this help in that regard?
This doesn't do anything for that. So basically this, the input-output function that they learned doesn't say anything about the validity. So how TypeScript does it is basically, it does a type check, so it kind of your manifest typing instructions of the types that you assign to variables and expressions, it checks that they actually do make sense. So you don't kind of shoot yourself in the foot by like mistyping different statements, or passing in a parameter to a function that doesn't really match the type. But afterwards, it's basically erasing all those type annotations that you actually put into the code. So TypeScript, I think, is relatively simple. I mean, I can say that I haven't written it or I haven't contributed to it, but it's a relatively simple. Like apart from the translation part is really simple because you're just erasing those extra annotations. But the type checking part is really non-trivial. How do you create like non-obtrusive, like gradual typing? Because some people might not like typing every single statement, but they want to make sure that when you're working with very complicated, say layers in TensorFlow or Keras, they want to make sure that all the NumPy array dimensions do match, but they don't want to be forced to actually like type every int and every string that they pass into a print function or something like that. And I know I'm using like Python examples in a JavaScript context, but that's because I'm more conversant in Python. But so that's the thing. Like I think the main challenge in something like TypeScript is the actual like that gradual typing. How do you make typing work and be useful to a certain extent without forcing people to actually annotate every expression with a type? For a language that was not designed for that, like functional languages are generally they have like very bounded, like very easily implemented type checking algorithms. So you can kind of minimally annotate your code, and every line, every program position is well typed. Whereas something like JavaScript is way more dynamic, or Python basically is the same. So yeah. So I think that problem, like the challenge wouldn't be this. Like the challenge would be the type checker part, because like stripping all the type annotations is, for the most part, like find and replaced with empty strings. So yeah.
Okay. Thanks.
So what's the criteria for judge how well the algorithm perform? Like a machine translation, you use some blue score or something like that. But what is this?
So no, there's no blue score in this. They just use accuracy, which I know is like, you know, if you don't have straight line programs, there's no one single like translation for any. Only straight line programs are like structured enough where you have one true correct translation. And yeah,
unit test cases.
Something like that. So the programs that they create, and we'll get to that. It's they can unit test. So the paper they refer to, they actually go and scour like a bunch of online projects that are both implemented in C# and Java.
That's good.
And they actually kind of do unit tests. But these guys didn't even bother with that. They just created like their own arbitrary made-up language and like, yeah. And so the programs are short and everything's like.
Is it functional correct or just the right syntax?
Yeah.
That's true.
What's the accuracy means here?
The accuracy for them, because they define their domain to be very limited, the accuracy is basically, did you produce what we had in mind for you to produce or not? Which is not really a good metric, because it could be semantically the same code, like input, output, the same code, but not even like look anything like what you had in mind as the, you know, anybody who has done like any sort of disassembly of compiler outputs knows that, you know, the code that you write and the black magic that compiler does to it are not related at all. So it's a much harder problem to actually like evaluate something like that. And they basically don't do it. They basically define their problem, define their experiment in a way that does away with all that concern.
It claim to be state of art.
Yeah. Oh, this is yeah. State of the art. I mean, who am I to say what's the state of the art? But so basically, this is kind of a segue to the tree LSTM paper, and because these guys don't make it clear at all, there's like 6 different significant variations of the tree LSTMs, how you combine the child nodes into the parent node, and do you kind of add up the state, or do you have individual combining functions, individual trainable weights for getting from the state of the children? So because here, for example, you have HL and HR concatenated, and CL and CR, which are the hidden and cell states, and TS is like the source token, so basically the tree node that they're working on. And I mean, concatenation basically doubles the size of your state each level up the tree you go. So this is not something you can do like, you know, your tree would be very non-uniform in terms of the state size. So you have to kind of combine these. There's ways of combining them, but you can sum them up, and there's advantages and disadvantages to all of them. So I actually read their code, and it's not easy. Believe me, it's a mix of Haskell and Python for some reason. So yeah, so I think they're using the binary constitution grammar tree LSTM cell. So the tree LSTM paper is basically built on the assumption that you're using the tree LSTMs for linguistics. So in linguistics, you have the dependency grammars that could be n-ary, so you could have actually n child nodes for like a parent node, whereas phrase grammars or constituency grammars are basically phrase heads, so the subject and the predicate. So the phrase head or the noun phrase, verb phrase. So you almost basically by definition restrict yourself to binary, and you can kind of, you know, special case everything, and it's kind of a very simple variant of that. The problem with this is you were assuming that the nodes are binary. So the tree is binary. So each parent node has 2 children. How do you kind of deal with that? You can do the left child white sibling, and the picture definitely explains it better than I can. So this tree has 3 nodes under A. Only the left one, the left branch going out of A, is actually a child branch. And then because D and E are, and obviously it goes to C, which is the first child, and D and E that are siblings of C, they go down the rightmost path from C. So D and E, because they're right children, we know that they're actually siblings of C and not actual like true children. So
sorry, stupid question. Can you give an example of what one of those nodes would be?
So one of those nodes would be, for example, this could be an if. This is the conditional. This is the block. And for example, the conditional could be, so this is like C, D, and E would be tokens. So X equals or double equals something.
Okay.
So yeah.
if D have a child, how do you know E is a sibling instead of a child?
The child of D would go to the left branch.
Yeah, if they have a child there, how do you suppose there's a child as a Z, right?
Okay, yeah.
But how do you know E is a sibling of D instead of just a child?
Whenever you have a right child in the binary tree, you know in the original tree it was a sibling. So you know this was a sibling to this, and this was a sibling to this, and by transitivity of the sibling relationship.
But I mean, so suppose D have a child, right?
Okay, yeah.
Yeah. So how do you draw the structure? You add
So the child would be the left child. If it has 3 childs, all the other childs would be added as siblings of that left child. So you know what I mean? So you have another branch coming out here, and like as many children as you wish on a linear path, on a linear tree or something, subtree. That's how it works. It's unambiguous. You have to definitely it takes some getting used to, but it's unambiguous. It's not. You can basically binarize every tree with every whatever like branching factor you have, and you'll get a unique tree, and you can kind of translate that for it.
Yes.
So yeah.
It also it's happened like the other way around too. Like you have different forms. Like if you use phrase structure grammar, you can have non-binary childs, but if you use CNF, Chomsky normal form, then you have to make it binary, and the way you do it is similar to this.
Yeah.
Sorry.
So the work they based their results on is using both. So it binarizes both the source tree and the target tree, and it's not really grammar aware. Because they are doing it grammar aware, they actually only use it for the source tree because it's not obvious. If you're binarizing the output tree, it's not really obvious. How are you gonna how are you gonna enforce, or how are you gonna enforce grammatical consistency without blowing up the size of all the categories, the tokens and terminals and non-terminals that you want to add? So
it's kind of like a peg as a subset of a CFG, right? Like it does a similar thing where you disambiguate it and force it to go in a particular direction so that there's no ambiguity in the form of the expression, right?
Exactly. Except that for pegs, it's kind of like it's kind of not ambiguous by definition, but then you don't know what language it generates. Like it's kind of the other, like you kind of push the complexity one way of the equation. So yeah, in a way. But yeah. So basically, we kind of start. So the tree LSTM part. It's there's take it from me that this is a function. So you have, instead of just having the previous node in a linear sequence LSTM cell, you have 2 children coming together at a parent node, and you have some way an LSTM cell of combining the hidden states and the cell states of the children and getting to the hidden state and cell state of the parent child, and you start bottom up from the leaves of the source tree. And because the source tree is binarized using this scheme that we mentioned, you can basically create an encoding pass on the source tree. And at the end of the encoding pass, you're at the root of the source tree, and you have the encoded hidden and cell context of the source tree. Once you're done with the source tree, you just push the source tree state and cell, so the hidden cell state, into a new queue. And that would be basically the genesis of your target tree. So your target tree starts off as a 1-node trivial tree with the state coming from the final state of the source tree. Now, you want to blow it up again. You want to expand this tree into another tree that generates the target. And this is kind of the crucial part. You still keep track of your source states as you were creating them when you were consuming the source tree, and you basically create an attention map. And basically, you get weighted combinations of the inner product of your current node of interest, say. So you start with the 1-node target tree. So your current node of interest is that 1 node. You start with that, and you and the state of that was automatically inherited from the final state of the source tree. And you basically create an attention mechanism with all the intermediate states that you came up, all the subtree states that you came up in the source translation process from, and you get a bunch of weights. So you combine a context embedding or attention embedding or source embedding as a weighted combination of all these source tree states. And this is in the source domain, if you will. So you apply like a 10H nonlinearity with a bunch of learnable weights to that one, because now we have, like, you know, if you imagine yourself at the beginning of target generation, we have the hidden in cell state because we inherited them from the hidden in cell state of the root of the source tree. But how are we going to generate a symbol? How are we going to generate a token? And that's the way we generate that. So we go from this, which is the source level embedding or the source level attention distribution over the hidden states, and generate a target hidden state or the target attention mixed attention vector, and use a softmax over that to generate a token, a target token. And now we have a token. The other part is how are we gonna, because, you know, we know for all but the most trivial of programs, our target tree is not going to be single node, so we have to have an expansion, blow up phase as well. How are we going to do that? And that's the subject of the next slide. So on this slide, I actually have to go through what the prior art, basically the paper, the 2018, the iClear paper that they based their results on did, because it's really kind of, you know, their work is a very minor variation, in my opinion, on that work. So they binarized the target tree as well, because they don't have any grammatical enforcement or any grammatical constraints, so they can kind of deal with that uniformly. And you generate a token with an attention mechanism. You have a separate EOS end of sentence token that tells you that you're done with the translation, basically how natural language translation, neural translation works. If you generate an EOS token, you're done. You know that that subtree is already kind of spoken for. You don't have to generate any new nodes. You don't have to expand. But otherwise, you have two other expanding LSTMs, and they have both separate, weight parameters that parameterize the LSTM, and you have another embedding parameter. So the target token, the parent token that you're generating these two children from, figures into the generation of the child LSTM state, hidden in cell state as well. So so if the parent state is something, and the parent token and the target space or the output space embedding or context embedding or attention embedding, whatever is ET, you generate a left and a right LSTM state and push those into the queue of nodes to be processed, and you continue this process until there are no nodes left. So that's basically how it works. And this is kind of a demonstration of that. So that's kind of the attention mechanism. It's not from this paper. It's from the original linear sequence attention paper, but kind of drives home the point that you're basically creating a weighted sum over all the hidden states of the tree, and then you do an inner product to see at each stage what is the part of the source tree that you must pay the most attention to. And this kind of demonstrates the part where you're kind of mid-translation, you're kind of expanding a node, you're generating all these states, de novo, basically creating those states, and then the attention and the tokens. The attention comes from the hidden state comes from the parent through to two LSTM cells plus a source token embedding, and basically that's how the entire thing is put together. And yeah.
Can I ask something?
Yeah.
So here you're trying to go from the left tree to the right tree.
Exactly.
So what you're doing is that you start learning the representation from the terminal nodes and go up until you reach the root.
Yes.
And since that's root, it has essentially the information from the whole tree. So that representation is essentially a faithful representation of the whole tree.
Combined with attention, yes.
Sure. And then you pass that representation to the root of your target tree.
You just directly copy, yeah.
Okay. And then I didn't get, what do you do then to expand the next tree?
So once you copy the state, you still have to have a and assume that this is done because it's done using a learned parameter. So you kind of learn a transformation from the source attention space to the target attention space, and this might be because the ordering constraints are different. If you have a prefix versus like infix, the translation itself wouldn't directly pardon the pun, wouldn't directly translate into the target space. You have to like do some nonlinear transformation on it to make it suitable. So it's another degree of freedom here. But assume that this is done with. You have the hidden in cell states. You want to generate a token, and you generate the token using a softmax on the target attention. Once you have the hidden in cell states and the token of the parent, now how you generate the children. Either the token that you generated using attention was an EOS token, you're done, you're not going to add to the queue. Or if it was not, you're going to take the parent states, so hidden in cell states, the parent token, though embedded into a distributed representation, and the parent context of the parent attention vector. And you have two parameterized LSTMs, one for left, one for right, and you generate your children according to that. So for your children, you again have both the hidden and the cell contexts. Now we can go back to here. You can generate attentions and you can generate tokens, basically. And this attention, this source attention, comes from, again, from the hidden state of the target multiplied by all the subtrees of the source. So you, again, generate that, and then once you have that, once you have the token, you can push the hidden cell states plus the token into the queue, and then whenever you pop it, you're going to do the same with that triple again.
So if I have a bunch of code in one language, so I initially, like, maybe I hit it with some kind of regex to pull out tokens, then an LSTM goes through it and outputs a bunch of like vectors or whatever, then a second LSTM goes through those to build that tree up until you have one thing?
No. The first LSTM and the second LSTM are both kind of tree LSTMs. So what you described is basically neural machine translation. So you kind of you reverse the output order. So you kind of start the start the output sentence. So if you're translating English to French, you kind of because you want to, you're using attention, but still you want to, when you finish the sentence, the context is most fresh in the state of your model for what ended the other the source sentence. So you kind of start generating the target sentence backwards. But that is like a linear structure. So you start at word number 1, go to like word number 2, up to word number n, and then you have your attention over the entire set of words that you've seen. This one's like basically the same idea, except for the fact that the sequencing of these state propagations, instead of being from left to right, it's informed by the tree structure of the source language.
Okay, so the tree structure is already built for you.
Yes.
Okay, I see. So
Well,
it's not.
in the source language, in the target, you have to generate.
You have to generate it. So yeah, you have to generate it until you hit the. So what basically prevents you from going into an infinite loop is the possibility of generating EOS.
Yeah.
So how many sets of LSTM do you need to maintain? Like in the source tree is 3, target tree is 3.
The source, how many? So the tree LSTM combination rule gets like 2 inputs and creates one output, but you have to maintain the entire source set of. So if your source tree was size n, which is generally like around twice the size of your source text, the number of tokens, because you have all the internal nodes that kind of collect together a bunch of terminals and like a bunch of tokens into like higher. So you have the number 25. So you have the expression 25 plus 6. This is an additive expression, so there's another like add XPR node 1 level up top. So if your source is like length 3, typically your tree would have like 6 nodes, and you have to maintain around 6 nodes of history to up until the end of translation, because you're at every step of the way you want to attend to a certain part of the source tree, because you never know, like, as in like the ordering constraints are different. So at any given time, at any given point in time, you might be translating a certain part of the target, like the source tree. So yeah.
I mean before expansion of the LSTM, because in RNN basically you just maintain one set of parameters, right? Because you go back again, so you still use the same parameters. But here
No, you're maintaining one set of parameters. Yeah, exactly. You're maintaining. So the left and right combination factors, like how they come together to create the parent state, are one and the same throughout the entire tree. But the hidden cell states you have to maintain in some buffer, because when you're translating, you actually have to refer back to them using the attention mechanism to actually know what you're trying to translate. What part of the source are you trying to translate at this moment in time?
You mean the left chat and right chat, you share the same parameters?
They share the same, the mechanism that combines two children into one parent is one and the same in the source tree. So just because I'm at the leaves, I don't give myself the liberty of learning a different like tree combining LSTM. It's one and the same all the way through to the root, but I learn those parameters. So the parameters are basically meant to be, to a certain extent, basically combining the meaning the same way they are in like a linear LSTM, combining the meaning from children to some sort of distributed representation or meaning for the parents.
So
But it's one set of parameters. Yeah.
But it's still one layer of everything. There's no up layers.
Yeah. There's one layer. Yeah, exactly. There's no multi-layer LSTM. Yeah. You can potentially like they don't use it, but you can potentially like make your one-step combining operation to be multi-layer, but they don't use that at all.
So the weights are shared across,
Across
the representations are kept in case you want to take a look at them while you're generating the program. Maybe you want to generate this if statement, so your attention tells you to look at if statement in the source, and you want to be able to have kept that representation to refer to.
Exactly.
Yeah.
Exactly.
Oh, so the attention spans over both source and target?
Yes, so this
The
seems
entire
to have
source,
two attentions. One attention for the encoder, which is on your source,
Yeah.
tells you which part of the source to look at, and there is a decoder one, which tells you what if generated.
How to transform. I think so. I don't. No, there's no. You don't really look at what you've generated so far, so that's one of the problems. You just transform, like non-linearly transform your source attention into your target attention. So it's not really. I don't like what you say makes a lot of sense, but they don't do it that way.
Yeah, I like what I say too, but
Yeah.
but I want to know. So what's E over there? So
E is like the embedding of the attention, or like the embedding. It doesn't really make sense. They use it as embedding, but it's actually like an attention weight.
And H prime.
H prime is like the target node state. So to a certain extent, you're right, but you're only looking at the local state of the node you're trying to translate. You're not looking back at the entire set of things that you've already
Only the
created.
last step.
Only the current step that you're working on.
Yeah. Okay. So still you're keeping some information.
Some context. Yeah, exactly.
Okay.
Which makes sense because you're trying to match the input to the output. So you want to see what part of the input embedding is actually relevant to what you're currently trying to generate, but you don't really. You might do some redundant work because you're not keeping track of what you generated so far.
Yeah, so could you elaborate a little more on the embeddings? I'm not sure if I got it. So where does it come from?
So this is the learned weight
I see.
matrix. So so you have the candidate target state. This is basically a bilinear form.
Yep.
Like a generalized inner product. So you create an inner product. You do like you do the exponential weighting mechanism. So obviously the weights are proportional to these inner products, and then to the exponentials of the inner products. Once you have this weight, you combine all these source hidden states according to their weight, to their alignment with what you're currently trying to generate, and you get a combined embedding that is
So
basically.
you sum over all the source embeddings?
Yes, because otherwise, if you want to attend to a certain part, it's non-differentiable. So that's a problem. This is supposed to be a very peaked distribution, like in ideal conditions, but it's for reasons of end-to-end differentiability. Obviously, you're doing an actual like mixed, continuous attention mechanism, which is like ordinary for attention. It's not anything that they've invented or like it's not a novel distribution.
So the embeddings, I could say, represents an overall picture of the source.
Yes.
Because you're summing them.
Preferentially weighted towards whatever is more relevant for what you're currently trying to generate. So yes. But this is, there's no theoretical or like no conceptual justification for this transformation, but it does kind of make sense because if the ordering of tokens and whatnot is different, you want to have, to the extent that you can definitely ascribe certain significances to certain positions in your source embedding, you might actually have to like shift them up a little bit if the target language has different ordering rules or different expression evaluation order rules and stuff like that. So this kind of takes care of that. the ES to ET transformation.
You talked about needing a strong inductive bias to enforce the syntactic validity constraint. It seems to me there's an implicit assumption that there's equivalence between the syntactic constraints in the source language and the target language. In a sort of standard neural machine translation setting, if there wasn't equivalence between sort of the two languages, you can fall back on something like pointer networks for representation of sort of an unrecognized or an untranslatable token. Does the paper cover any kind of discussion about non-equivalence of the syntactic constraints?
Doesn't really cover that, and unfortunately, now this paper doesn't really enforce that inductive bias because it's the prior art. So this is the paper from May 2018. Okay. This one's from July, so it's from this month. So this is like just giving some context. So these people don't claim they actually kind of respect any sort of syntactic constraints or grammatical constraints. But and also, even the evaluation set up in this paper and the paper we are currently going over, they use very simple, like, Java and C# are like basically morally equivalent. They are not like, they're definitely not very different languages.
In the Microsoft building.
Yes. Still, I stand by my statement. So C# actually way better, but no, seriously. But it doesn't have the garbage collection is definitely garbage, but other parts are pretty good. So
dig in deeper.
Let's move on.
Yeah, for sure. But sue me if you want. But yeah. So definitely their examples don't bear out the whole, they don't even explore that part of the space. So yeah. So this was prior art. In this work.
Question. In the target tree, how do you identify when you do decoding? Which one is left child, which one is how come you do the next code left child or right child?
So you have two sets of parameters for the left child and the right child, and you binarize both source and when you get your training data, you kind of binarize both sets of trees. You know which one's the left. In your ground truth, it's obvious which one's the left, which one's the right. You train the weights for the left one in a way that kind of respects that input-output relationship. Likewise for the right one. So that's enforced by the data.
So you just add one dimension of your data, tell you like a marker says 0 or 1, and tell you right or wrong.
I didn't get that question. Sorry.
It's just like you encoding your word there, and you put an actual bit there, tell you it's right. It's left child.
You have two sets of. I mean, you can definitely parameterize it as a bit, but you have like two separate LSTM cells, so two separate sets of weights and everything to treat. So yeah, like these are not tied weights or these are not shared weights. So this tries to enforce the input-output dependency on the left side children. This like if it's 0, if it's 1, for example, I mean it's arbitrary. It tries to enforce the regularities in the training data that you see with respect to a parent and its right child.
Oh, you have two sets of LSTM.
Oh yes, so the I basically is two sets of LSTMs. I kind of mentioned. Yeah. So so you have like the target tree is binary, and you have a left LSTM. So the I is basically the index into that. In this work, the target tree is kept n-ary because there's no way of the binary tree and the rigid grammar that we had for general like n-ary productions don't really go together well. So they actually might, but I don't know, and the authors definitely don't know either. So there might be some very clever combinatorial construction, but that I'm not aware of. But so for each source token, and token here is like generalized token. It's not the token in the source level language. It might be a non-term production of the grammar. We know from the grammar, we know the arity of the token. If it's like binary, if it's ternary, if it's whatever, quaternary, you can go as many branches deep as you or wide as you want. But for each of the n child positions, so for example, this requires some explanation. So for example, if we have an additive expression, the left side, and this is not the best example because the left and right are not super distinct, but the left side and right side could be numerical literal. So they might be the number 12. there might be variable references, so a reference to variable I, and there might be factors, so 2 times 3 times 4 times 5, which can sit in the left side, or the right side for that matter, of a plus expression, likewise a minus expression. So all things that can happen in the same context in the grammar are called basically a context. So you kind of a category, sorry. So you kind of factor out the categories in your grammar, and they don't really go into depth about how they do it, but I presume, and I'm pretty sure, we can prove it, that this is a finite construction. So from your source grammar, you can basically get all the different things or the different sets of tokens that can actually appear in any position, in any step of the tree building. So they basically know what would be, in the target language, what would be the set of legal children, or the category of legal children in any position in any production of grammar. And once you know that, your problem is basically solved. You learn a separate set of parameters for that category. So instead of, if you have k categories, you learn k sets of weights and intentions and all the shebang for creating the actual symbols from your parent tree state and token. And the entire mechanics is the same regardless. So instead of having one set of left-right child to generate the token, you have maybe 12, 13, 14, and they don't go into detail about what would be the typical blow-up, because I think if you go beyond toy languages, the blow-up's not going to be trivial. You might actually start with the grammar with I don't know, 8 productions and get 640 different categories, and then who's going to say you can collect enough data to actually learn all those parameters in any meaningful way? But they don't go over that, and their test data is really toy data. So I don't really trust this paper on that grounds. But you basically kind of do this, and another advantage of this mechanism is once you actually know, once you're operating at the level of the actual tokens or actual categories of tokens of the target language, you don't need the EOS symbol. That entire formalism is completely redundant, because once you're at the level of the language terminals, you know that you're done. You're not going to expand the number to any further, or the operator plus, or a function call. Once you get to there, your job is done. There's nothing else to be done. So they can kind of get do away with the EOS symbol, and this is basically the entire contribution of this paper, this one slide. So yeah.
Are they creating the categories from the training set, or is it
From the grammar?
Okay.
And they're completely, they don't go into any detail. I presume it's a manual process. You can probably automate it if you have the willpower, but to what extent it actually blows up the size of your categories that you have to consider, I suspect it does blow it up for any realistic grammar. So yeah. So
sorry, so why would it blow it up? Because you have, I don't know, k. You have things that take, I don't know, 2 inputs,
So yeah. So in some category K, you might actually have to have to be forced to so the power set of all the different terminals and non-terminals could potentially be the set of your category. So it's a subset, because in some contexts, numerals of variables and factors might actually appear together. So it's a 3 subset of the set of your terminals and non-terminals. In some other context, this and this might go together. So there's potential for exponential blow-up. And this they don't mention in the paper. I saw that in their code. They actually even add the possibility, and I don't know to what extent, what their simulations, what version of the code their simulations were using. They actually literally cheat by actually adding the parent context. So even if literal variable factor occur in as children of 3 different top level productions, so both additive expression, minus expression, and some other type of expression, so the 2 parameters to a function or whatever, or some unary operator, they actually give the ability of learning the even separate sets. So, which is, it's not doubly exponential, but it's even worse. So, and they don't make it clear at all. They don't report which version or which variant of the code they're using, but that's as much as I could actually glean from reading through their code.
So just to clarify, so for each softmax, at each time step, the decoding, you're not generating just, oh, is it a literal, variable, or factor, or all types of literals and variables and factors that could be. So that's why it's...
Yeah, so at a certain step, I know what the parent is. I know the parent is, for example, an additive expression production. And I know the additive expression production, for its left-placed child, it can take either a set of literal or variable or factor, and also for its right child, but consider for a minute that we're only talking about, so I know what subset of terminals and non-terminals are legal for each child position, and I have a separate weight, or I just name them as a separate category, and I have a separate set of parameters for that category. So, but I might actually parameterize the category with the parent itself as well. So if the sets are identical, but they're generated from different parents, which is what I was mentioning when I was saying it's going to be even worse than the power set.
I kind of like the idea.
The idea is pretty good. I don't know if it's if you're generating too many parameters for your own good. It depends on your data set size. So yeah. But so when you have as many LSTM cells and as many LSTM parameters as you have categories, you can basically feed those to generate the children's state, and then the same attention mechanism, the same softmax, basically generates the tokens for you. And this is my main gripe with this paper, the results. The entire work is a very slight variation on another work. They didn't have the decency to actually reproduce the entire set of experiments that the original paper did. So they actually went to the trouble of collecting a bunch of projects in C# and Java, as I mentioned, and testing their proposed method on that. These guys just went ahead and created their own phony language and their own phony data set, and basically everything is based on that. And the numbers they got for the method of the prior art was not even matching with their numbers. So that's that results section is an entire train wreck. So. And they actually use the naive sec to sec, and they make the argument that our their method, not our method, thankfully, their method is much more robust to random seam variations in the training runs that they actually train. But there's and they do they do report a sigma for their accuracy across different runs of the experiment and claim that this is much more varied performance compared to theirs. But I mean, take that with a grain of salt. I've spent a few days going through the paper and references. My opinion is that it's on very shaky ground. So yeah.
How does the number of tokens in the toy languages compare to real languages?
I would say this is a medium-sized function.
Yeah.
Not a not a full-fledged program by any stretch of imagination. So I leave the
I was specifically talking about the bottom line.
So this is the number of token classes basically. So
right.
variable, plus operator, minus operator, times operator, division operator, whatever, power, unary, minus, all that stuff. So this is what they mention, and these are so these are kind of not syntactic but lexical categories of the source and target languages. And the source language is basically 4, which is probably some toy procedural language or imperative language, and the target language is lambda. As is kind of obvious, it's the toy functional language. So yeah, this is their simulation results. So take that with a grain of salt, in my opinion, but I might be completely wrong, and this might take over the world in the next 3 years. So yeah, that's basically it.
Yeah, I have a question, because consider effectiveness of using LSTM, deep learning. Because you imagine you have some program in C# and another set of program to translate that program to Java.
Yeah.
It's very expensive, right? So how you need to have huge amount of data. So how?
That's one of the things. It's transpilation is definitely a thing. I'm not even talking about JavaScript and 2016, 2017, and later. There are a lot of tools that convert like all sorts of languages to other languages, but typically they have when you look at the output, it's not human readable. So supposedly a lot of older languages, if you were creating your own toy language in early 1990s, your best bet would be to generate a C version of your program, and or even Python in modern day, Python. Every Python programmer knows Python. I've had the pleasure of looking through automatically generated Python C headers and C code, and it's not anything like an actual programmer would write. So that's definitely a very relevant question. To what extent it's idiomatic code in the target language, and to what extent it's just syntactically correct, even maybe semantically correct, but completely non-useful in the sense that if you're touting this as something for computer-aided software engineering, and if you check in some code that was generated using this, and somebody filed a ticket about a defect in this software, I don't know. I don't really envy the person that has to actually fix that. So yeah.
So they didn't add any snippets of the codes in the page?
No, even all the pictures that you see here are fake. They don't. I mean, they might have done some simulations, but these are basically the equivalent. They literally picked up the picture from the other paper that they referenced and changed the graphics a little bit. But there's no indication that they did any tests on actual coffee script.
So this is a poster session.
Was it a poster session? I didn't really.
No, yeah. I'm asking because it's very short.
It's
like four pages.
It was in a track I think I remember the name of the track was neural program translation or something like that in ICML. I don't know if it's a poster session or
okay. Just to be fair to them, they left was it a GitHub link?
No,
it's a Dropbox. Yeah,
Dropbox.
that's actually so yeah. Partly I had to go through that code, and it's not really.
But it's just the code. It's not the input and output.
It's not reproducible at all. So you can. I mean, or it might be, but it's kind of hidden in 5 layers of. Yeah.
So I'm assuming this wasn't addressed in the paper, but I'm actually really curious if you, as input, provided multiple, effectively functionally equivalent pieces of code that were, differently, phrased, would you always get the same output? Because I'm thinking in terms of one place where if you were going to polish this in that way, straightforward human readable optimizations like removing loop invariants and things like that, you'd want to kind of have it tend towards that so that it would produce the most efficient human readable code, if you were going to actually kind of aspire towards that. But also I feel like depending on how they built the thing, you could make subtle changes that had no impact on the output of the actual running the code that dramatically altered the output of the transpilation. And I'm kind of curious about that.
They don't. So their metric is basically straight up accuracy, and I think they just kind of do bit for bit analysis, which is kind of unfair to the algorithm because for any non-trivial program you have many different representations. But I don't know. They probably something like that. I think kind of profile guided optimization, you kind of feed into it a gradual sequence of things that are semantically the same but more optimized in a direction that you prefer. You can actually kind of you can definitely guide the algorithm towards something like that, but it's not an area that they explore at all. I think I mean, to be fair to the authors, maybe the area is really novel, so it's not like it's a well-defined problem with well-defined data sets and competitions where the state of the art to 3 digits after the decimal and everyone's working on that extra 4th digit precision. So it's not really. Maybe in the next couple of years, people would explore different avenues of getting something like this in that context, a bunch of steps or gradual steps that a human might come up with, and how we can kind of basically nudge the algorithm towards that, towards more idiomatic or. That's the question, how do you even quantify idiomatic or more optimized until you actually profile and see how it runs? So that's kind of another, I guess.
Did you try generating it? They say there is a data set in experiment code.
I did not. This was done late
No,
last
sure,
night,
no,
so
no,
yeah,
no.
yeah, no, no.
Yeah, it's
There was
I'm
no
asking
time
for too much.
Yeah.
I wonder that, I'm not sure, for example, how deep or how wide is the normal tree, and then how deep the binaries run, and also, do you find the whole system kind of sensitive to the size of the trees in terms of performance or not? What do you think about it?
The results that have been reported doesn't really give us like enough information to really make a judgment on that. Like, you know, it might be, obviously the binarizing step gets your like, you know, broad trees and makes them into like very deep trees. But then to what extent, and you're learning one set of parameters, even if, because I presume, and there's an argument to be made, that when you're kind of starting bottom up, you know, once you're like near the leaves, or when you're near the leaves, you have a different set of concerns as opposed to when you're like near the top of the tree, where you have to like be more kind of, you know, a general like organizational principle, like how the pieces fit together, as opposed to just getting the local translation right. So it does make sense that this method might be very sensitive. Like if you run it on like trees that are going to be like 16 levels deep, it's not going to work at all, because by the time you get to the top of the tree, despite the fact that you've learned the embeddings and you've learned the child generator networks, the vast majority of the training samples that they've seen come from you know, further down the tree as opposed to like near the top, and you know, those are kind of different problems. So yeah, I don't like with yeah, again, with all
I
due
think
respect.
the reason that they use the attention is because they are trying to solve the issue of the depth of the trees. That's why they are talking the attention idea.
Yeah, that's a very good observation. Maybe to a certain extent, like attention definitely kind of attunes you to the part of the source that you are trying to replicate in the target tree. I mean, all of it, assuming it works, who knows what it's doing? You know, it's a very non-transparent, like non-explainable model. But yeah.
So related to that, is there like a max depth that these guys talk about that works?
As in max
Like
depth?
when you binarize, what's like the?
They don't talk about a maximum depth. But obviously, like, you know, when you look at their data set, you know, you can. It's almost an exercise for the reader to kind of understand if the typical grammar has like a branching factor of 3, and if you binarize the trees, like, you know, and if your longest.
All right. Thanks, Alex. One more.